to discuss constant rate of change. Here are the main points that will be addressed in the video. Please read these and think about them carefully as you watch the video. If necessary, write these down. The concept of constant rate of change is related to the relationship between two variables. If x and y represent the measures of two quantities, and y varies at a constant rate of delta y over delta x with respect to x, then the change in y is always delta y delta x as much as a corresponding change in x. A constant rate of change between x and y means that for any fixed amount of change in delta x, the corresponding amount of change in delta y are constant. So first, let's think about rates of change in the context of pouring water into a pitcher. Here's a cup that already has some water in it and a pitcher full of water. I'll play an animation showing the water being poured from the pitcher into the cup. As you watch the animation, think about the relationship between the height of the water in the cup and the volume of the water that is added to the cup. In particular, you will need to determine whether the rate of change of height with respect to volume is constant, increasing, decreasing, both increasing and decreasing, or something else. I'll play the animation now. Many people will say that the rate is first increasing and then decreasing because the top of water in the cup appears to rise quickly and then more slowly. But that perspective is comparing the height of the water to the amount of time that has elapsed. Here, we want to compare change in the height with change in volume. So it is important to pay attention to two quantities we want to compare. Here, we want to compare height and volume, not height and time. Height and volume. And it turns out the height of water in the cup changed at a constant rate with respect to the volume of water that is added to the cup. Let's think about why this is. First, we'll zoom in so we can see the cup in a bit more detail. Next, I'll represent the height of the water in the cup. I'll use black oval to show the water that was in the cup before starting to pour. I'll represent the height of the water that is initially in the cup using a green arrow. And I'll represent the change in high water in the cup using a blue arrow. Next, I'll represent the volume of the water that gets added to the cup using a red arrow. Let's rewind this to start of the pouring. Now I'll show this again. As animation plays, think about how the height, which is the blue arrow, the length of the blue arrow, and the added volume, which is the length of the red arrow, are changing with respect to each other. Next, I'll add black bars to indicate the change in volume. So the distance between the bars is showing amount of change in volume. We can copy this length onto the height bar. Now we think about the amount of change in height we can see that delta H is roughly 1 and 3 quarters as large as delta V. Let's rewind the animation. Let's play this animation again, this time incorporating the black bars to show amount of change in volume. Now, it's not the case that total height of the water was always a fixed multiple of change in volume. This is because the cup has some water in it before we start pouring. However, what you might have noticed is that no matter how large delta V was, delta H was always about 1.75 times as large as delta V. This is what it means to have a constant rate of change. In this scenario, height and volume vary at a constant rate of 1.75 with respect to each other if the amount of change in height is always 1.75 times as large as the amount of change in volume. We can also think about how this would work if, instead of treating the added volume of water as a single large part, we split our volume into two equal-sized parts. To make things a little easier to see, let's rotate the height bar It's still the case that for each of two sections of added volume, the amount of change of height is about 1 and 3 quarters times as large as the amount of change in volume. What if we had used different number of sections? Let's split the added volume into 5 sections. It is still the case that for each of the 5 sections of change in volume, the amount of change of height is about 1 and 3 quarters times as large as the amount of change in volume. This was true whether we split the added volume into 2 equal parts or 5 equal parts, and it will be true for any way of splitting into equal parts. So a consequence of our definition of constant rate of change is for every fixed amount of change in volume, the amount of change in height is constant. So now we have two ways to think about what it means for the height of the water to change at a constant rate with respect to volume of added water. So now let's look at another example. Let's think about filling a bowl with a frozen yogurt and the relationship with its cost. Here is a frozen yogurt machine. You fill a cup with yogurt and then get it weighted. It costs 59 cents per ounce. Since the cup weighs about half an ounce, you end up paying 29 cents for just the cup, plus the amount for the yogurt. Next to the cup is a scale that shows how much the yogurt will cost. It already shows a cost of 29 cents for the cup. I'll play an animation showing frozen yogurt being dispensed into the cup. As you watch the animation, think about the relationship between the weight of the frozen yogurt in the cup and the total cost. In particular, you need to determine whether the rate of change of total cost with respect to weight of yogurt is constant, increasing, decreasing, both increasing and decreasing, or something else. I'll set the animation now. The answer is that the total cost changed at a constant rate with respect to the weight of frozen yogurt that is added to the cup. Let's think about why this is. First, I'll represent the total cost. The green arrow represents the cost of the cup itself. And I'll represent the change in the cost using blue arrow. Next, I'll represent the weight of the frozen yogurt that is get added to the cup using a red arrow. Let's rewind this to the start of the dispensing. Now I'll show this again. As the animation plays, think about how the weight of the yogurt, which is the length of the red arrow, and the additional cost, which is the length of the blue bar, are changing with respect to each other. Next, I'll add black bars to indicate the change in weight. So on the bottom, the distance between the bars is showing the amount of change in weight in ounces. We can copy this length onto the cost bar. Now, if we think about the amount of change in cost in dollars, we can see that delta cost is roughly 0.59 times as large as delta weight. Let's rewind the animation from the beginning. Let's play the animation again, and this time incorporating the black bars to show amount of change in weight. Now, it's not the case that the total cost was always a fixed multiple of change in weight. This is because we had to pay for the cup before we start to add any yogurt. However, what you might have noticed is that no matter how large delta weight was, delta cost, measured in dollars, was always about 0.59 times as large as delta weight, measured in ounces. This is what it means to have a constant rate of change. In this scenario, total cost and added weight vary at a constant rate of 0.59 with respect to each other if the amount of change in cost is always 0.59 times as large as the amount of change in weight. We can also think about how this would work if instead of treating the added weight of frozen yogurt as a single large part, we split our weight into two equal sized parts. To make things a little easier to see, let's rotate the cost bar. If we compare the lengths of the arrows in each section, we can see that the amount of change of cost is about 0.59 times as large as the amount of change in weight. What if we had used different number of sections or different number of parts? Let's split added weight into 5 sections. It's still the case that for each 5 sections of the change in weight, the amount of change of cost is about 0.59 times as large as the amount of change in weight. This was true whether we split the added weight into 2 equal sections or 5 equal sections, and it will be true for any way of splitting into equal sections. So a consequence of our definition of constant rate of change is for every fixed amount of change in weight, the amount of change in cost is constant. So now we have 2 ways to think about what it means for the cost of the yogurt change at a constant rate with respect to the amount of added weight. If we think about the examples we've seen, we can summarize the notion of constant rate of change in the following way. Two quantities vary at a constant rate with respect to each other if changes in their measures are proportional.